Hello, for this video we'll talk about Einstein's law for velocity addition. So from classical physics and from daily experiences really that when you walk, let's say you have a rate of 1 meter per second, your speed of walking. When you walk at that speed and then on top of a moving platform, let's say moving at 2 meters per second. So when someone like not on the platform observes you moving, okay, what he sees is the sum of your speeds 1 plus 2, which is 3 meters per second. So even though that you're only moving at 1 meter per second, someone not on the platform will see that you're faster. That's why sometimes if you notice, it feels weird to be moving on the walking on the platform and then look at the sides, because what happens is that our brain is sort of programmed to have a feel of how 1 meter per second speed looks like, and when you're walking on the platform at that speed, you look out, it seems faster. So there's that disconcerting feeling. But anyway, this has been, we know this, we see this from our daily experiences, but this is actually not the case. So in general, the velocity that we see being the sum of let's say the velocity of the platform and your velocity while you're moving, that's not actually the case for very large velocities. And in fact, Einstein showed us that this is just an approximate this velocity addition, okay, which was of course known during the time of Galileo. And what he did is he found the correct way to add these different velocities, okay. And typically when we teach that, at least the way I derive it when I teach physics 73 to non-majors, we usually start with Lorentz transformation. So Lorentz transformation relates displacements in time intervals between two observers, okay, moving at some relative velocity, let's say, I don't know, v1, for example, right? So this is given by gamma delta x prime. So again, delta x is the displacement as observed by some observer in one reference frame. Delta x prime is as observed by another observer, let's say, on riding that moving platform in our example above. Okay, so this is gamma delta x prime plus gamma, let's say the velocity of the moving platform or racket or whatever that you're riding is v sub 1, okay, and delta t prime, and of course the time elapsed that will be observed by the reference frame, let's say, that is on the ground, will be given by gamma delta t prime plus gamma, the velocity of the other reference frame relative to the first one, delta x prime. Let me see. Wait, I think there's let's not work in natural units. So I believe there's a c squared factor there. Okay, but basically what we do is, when we derive this, is that the velocity that will be seen by an observer, let's say, that is not on the platform, will be basically, let's call it v, okay, like this v here, will basically be the displacement that object that is looking at took, divided by the time interval it took for that object to move. That's by definition the velocity. And if you use the Lorentz transformation, you're just dividing it, okay, the Lorentz transformation for delta x and delta t, delta x prime over c squared, okay. And if you'll notice, all the gammas, these are the Lorentz factor, but they'll just cancel out. This will give you delta x prime plus v1 delta t prime over delta t prime plus v1 delta x prime over c squared, okay. But the thing is, so the velocity that the guy on the ground sees is delta x over delta t. So let's call the velocity that the guy on the platform if they're looking at a common object, for example, let's label that velocity that he is seeing as v sub 2, okay? So therefore, v sub 2 by definition is given by the distance that an object travels according to the guy on the platform, let's call it delta x prime, over the time it took for it to move, delta t prime. And I wrote it that way so that I can simplify this equation. If you divide the numerator by delta t prime, this will give you v2 plus v1, okay? And then the denominator also, you divide it by delta t prime, this will give you 1 plus v1 v2 over c squared, okay? Or we can rewrite that v1 plus v2 over 1 plus v1 v2 over c squared, okay? So this is actually the correct velocity addition formula, and note that it is not exactly additive, okay? You don't just add v1 and v2. However, for instances where v sub 1 and v sub 2 are very much less than the speed of light, so the term here in the denominator, if v1 and v2 are very small compared to the speed of light, which is 3 times 10 to the 8. So typically, our speeds when we like walk or we are on platforms, they are very, very much less than the speed of light. This term here will be negligible, and that's when we go back to the old, our Galilean or our usual experience that the velocities they seem additive. Okay, but here's a so the point of this video is that let me show another fascinating way of deriving this. If, for example, you don't know Lorentz transformation, okay, you don't know these transformations, but you do know the fact about the postulates of Albert Einstein in his special relativity, in particular the postulate about the constancy of the speed of light. The fact that if something is moving at speed c, anyone who is observing it, regardless of whatever reference frame they are, will always find that the speed c. Okay, so let's look at this v. Okay, the velocity that one observer sees. This is a function of v1 and v2, and of course this is the exact form. Let's pretend that we don't know this. Okay, so that I can show you another way to arrive at that. Let's pretend we don't know this, but we do know that at a very small speed, it will reduce to v1 plus v2. Okay, so now we will have some factor here, some function of v1 and v2, such that when v1 and v2 are very much smaller compared to c, it will reduce to merely v1 plus v2. Okay, so how do we find that f? How do we find the form of that function? Well, let's look at the asymptotic limiting cases. Okay, when the objects that we're looking at travel at the speed of light, or they are light themselves. Okay, so if that means if v1, for example, the object we're looking at, let's say, is v1, it is light, let's say. So if it is traveling at the speed of light, according to the light postulate of Einstein, the guy that will be looking at that light will also see the value c. Okay, and he will also, from his point of view, the speed of light will also be a constant. Okay, so therefore, okay, for that case, for this to be true, okay, for this to become c when v1 is equal to c, it's easy to see that f should have the following form. Okay, f should have the form c over c plus v2. Why? Because, or we can rewrite this, let me divide it by c, numerator and denominator. This will give you 1 over 1 plus v2 over c. Okay, but why should we want that? Because if we have that form for our f, then v of c v2 will be given by c over c plus v2 multiplied by v1 plus v2, but v1 is c plus v2. This will cancel, and indeed it is equal to c. Okay, so in the limiting case that v1 is equal to the speed of light, this f has a functional form 1 plus v2 over c. Now, for a similar reasoning, if let's say they're looking at the other object, okay, or the guy who was observing in the first scenario was moving at the speed of light himself, right? So therefore, if v2 is equal to c, then the observer who was like on the ground should also see that he, the one that he is observing is also moving at the speed of light, whatever the speed of v1 is, okay? So again, v1 observes that the other objects moves at the speed of light. Therefore, according to the constancy of the speed of light postulate, this observer will also see it to be moving at speed c, okay? So therefore, our functional f, v1 of c, in order for this to be true, should have the form c over v1 plus c, or we can write that as 1 over 1 plus v1 over c, right? Now, what if v1 and v2 are both moving at the speed of light? Okay, so it's like light observing the other light is also observing the other light. Then the guy on the ground, regardless of who's observing who, should also see them moving at the speed of light. In other words, v of c should also be equal to c, okay? So therefore, in order for that to be true, f should have the form, if both v1 and v2 are equal to c, f should have the form c over c plus c, which is equal to 1/2. Okay, why is that the case? So that, okay, so that when you let when you let both v1 and v2 equal to c, then this will be equal to f, which is 1/2, multiplied by v1 plus v2, which is 2c, and indeed that is equal to c. Okay, so let's write those limiting cases. So this function that we don't know of v1 and v2, let's summarize. It behaves as follows. When v1 is equal to c, okay, when v1 is equal to c, it looks like 1 over 1 plus v1 over c. When v2 is equal to c, it behaves like 1 over 1 plus v2 over c. And when both of them are equal to c, it behaves like it becomes 1/2. Okay, and if you study those behaviors, it's not difficult to see that a function that could satisfy all of those, when you let the other v equals c, you get this remaining. Okay, and so it's not hard to see after a few minutes of reflection that my function should have the following form: v1 v2 over c squared. Why? So that when I let v1 equal to c, this will become 1 over 1 plus v2 over c, right, which is this one. If I let v2 equal c, then this reduces to this. If I let v1 and v2 both be equal to c, then this reduces to this. Okay, so therefore our original v, okay, as a function of v1 and v2, which we said is some function of v1 v2 multiplied by the asymptotic case when both of them are very much smaller than the speed of light. So in other words, f should be equal to 1 when v1 and v2 is very much smaller than c, which is the case here, right? So therefore, the velocity addition law with those asymptotic limits will be equal to v1 plus v2 over 1 plus v1 v2 over c squared. Okay, which is, and the awesome thing is, this is also the one that we've derived here, okay, on top, but with the knowledge of the Lorentz transformation law. Okay, so even with that knowledge of the limiting cases, starting from the fact that if one sees something moves at the speed of light, then any other observer should also see it moving at the speed of light, is actually sufficient to derive this velocity addition law. Okay, so I hope this video has been useful, and thank you for listening, and I'll see you next time.